mean, it's easy to say, for example, in this middle interval from here to here, what are the x values? Right? Where does this thing start to decrease? At -1, and it stops decreasing at, no, x values at 1, right? So you would say this is the interval of decreasing right in there, which you have to say in one way or the other. You know, the easiest way, which we saw in the first chapter, is a three-part inequality. You could say it's decreasing from -1 less than or equal to x less than or equal to 1. Right? That's where it's decreasing. Now, it's increasing over here. Right? Now, how would I describe that interval? I could definitely see where it stops increasing, right? It stops increasing here at -1. But where does it start increasing if that line goes on forever? You would say that it starts at -infinity, right? Because the extreme side of the number line goes towards -infinity. I'm not sure how they would say it in this class, because mostly, again, in pre-cal, we would do it just a little bit different. But you might say that it's increasing for increasing x less than -1. And then how could I say this interval of increasing? From here onward, x is greater than 1. Right, so those are intervals of increasing and decreasing. Let's see, I got to change my color scheme here. Oops, not there. Let's try highlighter again. Okay, how many intervals of increasing do you see on this one? Yeah, how many different places on the graph? You see it increasing from here to here, right? And from here to here. Right? And you see it decreasing, let's choose a different color this time, decreasing here and here. Because from left to right, it's going down, going down. Now, how would I describe those intervals? Right, let's say the decreasing I'll put on the top. Right, it is decreasing for x less than, what is the x value? 1, 2, 3. -3. X less than -3. And then it's decreasing in between these 2 points, which you would say time for a three-part inequality starts at 0. It's less than, x is less than 1, 2, 3, 4. Those are the decreasing. Right? How can we describe the increasing? Here's an interval of increasing. What are the x values on either side of that? Try again. -3 to 0. -3 is less than x is less than 0. How about this one? It starts here and it goes to the right. How are you going to say that? How about x is greater than 4? Notice that here we said it's decreasing from 0 to 4. And here we said it's increasing for more than 4. What's it doing right at 4? It can't be increasing and decreasing, right? So it's not doing either. So we should actually always use not or equal to when we do that. Just make it like that. And I made a mistake when I did it here because I used the or equal to. Ooh, that's way too big. I should have made that just a regular old less than. Okay, how about a linear function like that? What's that one doing? It's always increasing, right? There is no decreasing. So I'm not sure how they would say it. You could say it's all real numbers. When we get into pre-cal kind of terminology, which we could use here too, we would say it's increasing from -infinity to +infinity. right? From all the way on the left to all the way on the right, increasing. And how about a parabola like that? Where does it look like it changes direction? Yeah, I'm saying from up and down. Where does it stop increasing and start decreasing? Yeah, I tried to make it like 2, but obviously it's hand drawn, so it's not very good drawing. I'm going to go up here like this, increasing, 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 stop increasing, start decreasing, like that. So we would say this one is increasing. How would you describe these x values? X is less than 2. And the decreasing is x is greater than 2. Right? So that's the concept of increasing and decreasing is just showing where does it go up, where is it going up, where is it going down, and you always say that in terms of x. Right? You don't look at like this value here and say -2. The -2's got nothing to do with it, right? So don't give the y values. It's the most common mistake is you try to give y values when it means x values. The end behavior, another thing we didn't used to teach in this class, but I'm supposed to at least address it, so I will. The end behavior is like describing what is this doing on the right side of the graph. As x increases, what is the graph doing? Is it increasing or decreasing? It's increasing, right? Now, the book, which we could see in the homework that we just went over, that's what all of this stuff was describing right here. They just say up. Up on the left, up on the right, up on the left, down on the right. That's not the terminology that I've seen used in the past. Most of the time, we would say something like, as x approaches infinity, meaning goes to the right, then it looks like y is approaching infinity. And I'm pretty sure that's the way the SOLs had it in the one release test that we've seen. They don't just say up and down. I think that's very much our textbook. Now, as x approaches negative infinity, what is this graph doing? It's going down, right? So it's going towards negative infinity, right? So y values negative down here, you would say y goes to negative infinity. Right. What is this one doing as x approaches negative infinity? It's going towards infinity, right? Positive infinity. Or you could just say up, right? This one is up and up. This one is down and up. This one is down and down. In the pre-cal book, they say it like this. Falls on the left, rises on the right. Rises on the left and right. Falls on the left, rises on the right. Falls on the left, falls on the right. So, I mean, you see all the different terminology for that. So, increasing, decreasing, end behavior. And the last thing is zeros, right? And zeros is really the topic of the lesson today, right? Zeros are the x-intercepts of the graph. So if you look at this first cubic right here, how many x-intercepts do you see? How many places does it cross the x-axis? 3, right? So by zeros, we mean where does the graph cross the x-axis? There, there, and there. And since that's a cubic, that's the most you could have, right? You can have up to 3 zeros. This is a quartic. How many zeros does it look like it has? Yeah, it has 1 here. It's got 1 here. It's got 1 here. Those are zeros, right? Again, and the reason why they're called zeros, these are graphs of functions, right? Y equals and some expression on the other side. But what is the value of y on the x-axis? 0. So that's the zeros are the values of x where y equals 0. That's what it means. But they're also called x-intercepts. Sometimes they're called solutions. Sometimes they're called roots. There's all kinds of words for this. How many zeros do you see in a linear function like this? just 1. Remember, its degree is 1. It couldn't have more than 1. And how about this one? It's a quadratic. How many zeros do you see? 2 right there and right there. Right, so zeros are the values of x when y equals 0. And where does y equal 0? On the x-axis. So basically, they're the x-intercepts. You graph and you look for where it crosses the x-axis. Or in this case, it doesn't cross the x-axis, it just touches the x-axis. That's its own particular case that we get to at the very end today. Okay, I think that's enough of that. So I'm going to skip the second page. Maybe we'll look at it next time. So find the zeros of a function. Okay, so again, by zeros we mean the values of x when y equals 0. So if I substitute y equals 0 here, that changes what was a function into an equation. Okay, now we can use the same property that we used in chapter 4 with solving quadratic equations. When you've got it in the factored form, if the product equals 0, that means one of the factors equals 0. So you just have to say to yourself, which value of x would you plug in to x plus 2 to make that one factor equal 0? -2. So the solutions are going to be -2. How about the second factor? +1, 1 minus 1, and +3, right? So the zeros are -2, 1, and 3. Okay, you done, Dee? Now, if you looked at the graph, you know, what do you notice here? There's our zeros, -2, 1, and 3. Notice the x-intercepts on this graph. Where are they at? -2, 1, and 3. Right? So I graphed this. I put it on the y equals in the calculator in that form, just like it with all the parentheses and everything. And I let it graph it, and there you can see. Right, so notice there's 3 different things going on here, right? First, we have the x-intercepts. Actually, maybe 4 things. Then you have your zeros, right? These are called zeros right here. Right, these are called linear factors, right? Linear factors. Right, and this is the function in factored form. I mean, we know what standard form is. We did that in the homework last night. But that would be a factored form. So what's the relationship between a 0 and its linear factor? If 1 is 0, the linear factor is x minus 1, right? If 3 is the 0, then the linear factor is x minus 3. Now, this one here may look a little different, right? Because it's -2 and x plus 2. But it's really the same thing, right? This x plus 2 is really x minus -2. So the linear factor is x minus the 0. Right. Okay. But if you had x minus -2, you wouldn't write it like that. You're just going to change the minus and negative to a plus. So when you see a plus, that means -2 is the 0. You see a minus, then +1 is the 0. I should put on here, in case. By zero, I don't mean the number zero. I mean the zero. Okay. I think that was a extra slide. I don't know what happened. Okay, so let's see. If I have zeros of -4, -1, and +2, what are the linear factors? No, remember the linear factor's got an x in it. Okay, so this would be x plus 4. What's next? X plus 1, x minus 2. Okay, so what would be the function? Y equals x plus 4 times x plus 1 times x minus 2. Right, so you change zeros into factors, and then the factors, in factored form at least, that is the polynomial function. Okay. Okay. How about if I've got the factors? How can I tell what the zeros are? Here's the linear factors. What are the zeros? -5, -3, and +6. Okay, what is the function? Right, and x minus 6. Right, so you should be able, if you got the zeros, make the linear factors, or if you've got the linear factors, write the zeros. That's one of the SOLs, right? That you understand the relationship between those two. Good. Okay, so go ahead, try to turn those 3 zeros into factors and into a function. What are the factors? Okay, so you're going to say the first factor, I'm sure almost everybody said x minus 0, right? And then what was the next one? X minus 9 and x minus 10. Okay, but you would never leave it x minus 0, because what's x minus 0? X. Come on. Holy mackerel. X minus 9 times x minus 10, right? Which is important, because one of the main mistakes we make when we do this is that we don't recognize that when we have a factor of x, that the 0 is 0, right? That's like saying there is an x minus 0 there. We're just not writing it. So when you have a factor of x, you got a 0 of 0. Yeah. I will accept it from you guys, but you shouldn't be doing it. Okay. You'll never see that on the SOL. You will never see that in the SOL. They're not going to write x minus 0. No, never. You'll never see x minus 0. You just see the x. So what is the function again now? And what would be the degree of this polynomial? Well, I mean, what would be the highest power of x? If I did multiply all these three things, the highest power of x would be cubic, right? It would be x to the third. So when you've got 3 zeros, then you're thinking cubic, right? Right? So next step is, what if what you've really got is a graph? Okay? How can I turn that graph into the zeros? What are they? Right? Okay, so if those are the zeros, what are the factors? Just say the x, right? And then minus 2. And, you know, you wouldn't leave the x in the middle there. I'm sure you'd write it first, like x times x plus 2 times x minus 2. So what is the function? Y equals. Right. So we should be able to go from a graph, take the zeros from the graph, write the zeros and the linear factors, and then we've got a factored form of a function. I think the next one is for you, I think. Try that one. Turn the graph into zeros, the zeros into linear factors into a polynomial. What were the zeros? Negative 3 and 2. So what were the linear factors? So the factored form of a function would be y equals x plus 3 times x minus 2. Now, if I said put it in standard form, what would you have to do? FOIL. You'd have to multiply them, right? Remember, standard form has no parentheses, got the highest power term on the left, descending order of powers, right? So we could make that into a standard form by doing the multiplication. Let's see what's next. Surprise myself. Okay, so now, the function, if it's not in the factored form, you may still be able to find the zeros by graphing it. So let's put that in the calculator and see if we can find the zeros by looking at the graph. Clear. X to the third minus x squared minus 12x zoom 9. So I got the second y equals. You might want to go back to your stat plot and turn off the plotting of points so that you don't have to look at the points. I think I'll just leave it like that. I think you guys can see that. You should get a graph that looks something like that. So what are the zeros? Yeah, it looks like negative 3, 0, and 4 from the graph. Okay, so what does that make the linear factors? X plus 3 times x minus 4 times x. Okay, so and what would have been the factored form of this function? Y equals x times, right? So the first part of the first example in the textbook was take this thing here and find the zeros by factoring, right? But you've already done that. You put it into the factored form without actually having to factor at all. You just went to the calculator and found the zeros, turned them into linear factors. This is the factor. That is like you went through and factored it. So you saved yourself a step of factoring, which I know is not your favorite thing to do. Okay, try this one. Find the zeros and the factors by looking at the graph. Anybody get zeros? So there's a zero, there's a zero, there's a zero. What's the values? Up, you got everything in the exponent. You have to start over again. After you do the x to the third, you need to right arrow out of the exponent. And that looks crazy. You got everything in the exponent. So after you do the x to the third, you got a right arrow so it gets back down to the line, right? Did you get it? Yeah. What is that? Negative 3, 0, 5. You got it. There you get the camera. What are the zeros? Yeah. Negative 3, 0, and 5. Right? If you just put that in, look at where it crosses the x-axis, you would have found those zeros. And then turn them into factors. I mean, even if, for example, like you just had a factoring problem. It said, factor this expression, right? Well, you could just look at the graph and find the zeros and then turn them into linear factors. That might be the factored form. I mean, this expression factored without factoring. You just found the zeros, turned them into linear factors, and it's like you did the factoring. Okay, what's next? I hardly remember. Okay, what is the cubic polynomial function in standard form with the zeros, negative 2, 2, and 3? Okay. So we've already been doing this, right? We've been taking zeros and writing the factored form of the function. Now we got to write the standard form. What's the first step? We take the zeros and we turn them into the factors, right? And the factors in this case are going to be x plus 2 times x minus 2 times x minus 3. Okay, now if you want to turn those into standard form, then you've got to multiply. Just like in the one I showed you where he said it was a FOIL, we would FOIL. But when you've got 3 binomials, you can't FOIL. What you got to do is just pick 2 of them and FOIL. And then you'll take that result and multiply by the one you didn't already use. So I mean, I'm going to do it in a way because I don't want to see too much simplification. I'm going to multiply these right here. I'm going to FOIL those two. Right? That will give me x squared minus 3x minus 2x plus 6, which is x squared minus 5x plus 6. Right, so now I still have to multiply by the x plus 2. Right, so if you've got 3 factors, you're going to have to just take 2 of them. They're all, these linear factors are always binomials. So you take 2 of them and you FOIL. And then you take what's left, which is probably a trinomial, and multiply it by the binomial you didn't already use. Now, FOIL would not work here because FOIL gives us 4 terms. When you multiply 2 terms times 3 terms, how many terms do you think you're going to get? 6 terms, right? So that FOIL does not work. What you could do is you could just like go through, multiply x times everything here, multiply 2 times everything here, combine all the like terms. There is a method that I usually show, which you may find convenient or not, it's up to you. In one way or the other, you've got to figure out how you multiply everything in this set of parentheses, the binomial, times everything in that set of parentheses. And this is what the way we've done this, right? You make yourself a little grid, right? On one side of that grid, I'm going to put the x plus 2. X plus 2. On the top of it, I'm going to put the x squared minus 5x plus 6. And then I'm going to fill in the grid by multiplying what's at the top and the left of that cell, right? So like in this one right here, it's going to be x times x squared, which is x to the third. Right. And this one, it'll be x times negative 5x. Negative 5x squared. X times 6. Right. 2 times x squared. 2x squared. 2 times negative 5x. Negative 10x. And then 2 times 6, 12, right? So we made our 6 terms, but just like when you FOIL, there's some combining of like terms to do at the end. We got some combining of like terms. We have 2x squared minus 5x squared. Those are like terms. And we've got negative 10x plus 6x. So when I put all those together, the first term is x to the third. The next term is minus 3x squared plus or minus 4x plus 12. No, I did not. I taught a kid a few years ago here who had learned that from a teacher in Germany and showed me. And you guys are probably too young to remember him, but he died of cancer a few years ago. Mm-hmm. Okay. So I'm going to show you another way you can do that same thing, right? Because we make a lot of mistakes doing that thing right there. Sorry. How many points does it take to make a line? 2 points, right? 2 points determine a line exactly, right? If you know 2 points. Okay, well, it turns out then, as the degree goes up by 1, you need 1 more point, right? If you have 3 points, there's only one parabola that can go through those 3 points, right? Right? If you have a cubic, how many points do you think you're going to need? 4 points, right? Meaning if you have 4 points, there could only be 1 cubic function that goes through those 4 points. And the same thing for a quartic, right? If you know 5 points on it, and it can be 5 points, like right in a row, it doesn't make any difference. You know, if you've got 5 unique points from a quartic, there is only 1 quartic function that goes through all those. So with that in mind, doing that same problem that we just did, find a cubic polynomial function in standard form with the zeros, -2, 2, and 3, right? Turn those zeros into their linear factors and put them at y equals, right? We've already been doing that in the class, right? So that'll be x plus 2, x minus 2, x minus 3. Okay, go to the table of values, right? Second graph. And because it's a cubic, how many points do we need? Try again. For a cubic, how many points do you need? 4, right? You need 1 more than the degree. Remember, a straight line is a degree of 1, you need 2. So grab any 4 points from that table of values, any 4, right? I just took the first 4, 0, 1, 2, 3, 12, 6, 0, 0, and then I went to the stat edit and I put those 4 points. All right, okay. But you could take any of the 4 points. Just take 4 points, and what are we going to do now? We're going to make a cubic model that goes through those 4 points. Right, so once you've entered in the 4 points, then go to Stat Calc 6 for cubic, and this is your result. Right, and now you just plug in for the A, B, C, and D. And that's the same thing we got by doing the whole grid and everything. So at least up through quartic, you can do it yourself, and nobody's ever going to ask you to do something more than a quartic. I mean, I think you guys are actually fairly proficient right now at putting data in the calculator and finding the model, so that's an option for you. I'm not sure if I got another like that here. So try to do the same thing with this one, right? Just the way I did it right there. Turn those zeros into their linear factors and put them on the y equals line. Right. What are the linear factors going to be? It'll be x minus 3, x minus 3, x plus 3. Right, so put that on the y equals. Go to the table of values. We're making a cubic, so how many points do we need? 4. Grab 4 points. Write them down on a piece of paper somewhere. Put them under stat edit. Find your cubic model. While you do that, I'm going to do it the long way, okay? So I got x to the third minus 3x squared minus 9x plus 27. Did you get that? So you have a way to get it without actually having to do that work right there. And it's presumably we already know how to make our models, so it works. Okay, we're almost done. It's a long lesson. Okay, now that last function, right, this last one here, if I rewrite that, because I had x minus 3 twice, that's x minus 3 squared, right? And if I look at it on the graph, you know, you could put it in your calculator, look at the graph. This is what it looks like. How many zeros do you see? 1, 2, right? 2 zeros. Okay, but they don't look the same, do they? In this 0, the graph goes right through the 0 to the other side. But on this one, it just comes down and touches the x-axis, and then it goes back in the same direction. Okay, that's what happens when the 0 comes from a factor which is being squared. Because what happens when you square something? If you square a positive, you get a positive. If you square a negative, you get a positive, which means once it gets on either side of that value, it doesn't change sign. It keeps the same sign. But when it's to the first power, right, if I have a value of x which is less than -3, then this is negative. If I have a value of x which is more than -3, then it's positive. It changes sign. But when it's squared, it doesn't change sign. So when you're looking at a graph, if you're trying to find the zeros by looking at a graph, when you see this, you know you're supposed to write the 0 twice. Right? That would be 3, 3, and -3 because of the shape of the graph. Right? So when this number right here, when the factor is raised to a power higher than 1, that's called multiplicity. It means it has a multiplicity of 2. Right? When factors So that has a multiplicity of 2. So we're going to look at one more, and then that's it. So again, look at that graph and tell me what are the zeros. Okay, -3 and 2, but what do you know because of the shape, the way that graph does not cross the x-axis? It means that it's -3, -3, and 2, right? It means that the -3 is a 0 twice. If you didn't write it twice, right, then you wouldn't get enough linear factors to make the polynomial. I mean, we know what is the shape of this graph? What kind of function has that shape? It's a cubic function, right? We've got to have 3 linear factors, right? That's why you've got to write the -3 twice. So this will be x plus 3 squared times x minus 2. So the function is y equals x plus 3 squared times x minus 2. Right. If you're asked, like you're given a function like this, which you are in the homework tonight, if you're given the function and it says, what are the zeros and state the multiplicity, right? You would say the 0 is 2 and -3 with a multiplicity of 2. Okay. The multiplicity comment doesn't go with the 0 of 2. It only goes with this one. You got to be specific, right? Don't just say, it's not like a blanket statement for all the zeros are multiplicity 2. It's the one that is raised to the power. That's the only one. Okay. That's a lot of stuff. So if we go back over this now, the increasing and decreasing we talked about. We talked about zeros and intercepts. We really didn't talk about domain and range. Zeros of a function, describe the relationships between the zeros of a function and the x-intercepts of a graph and the factors. We did all that. Right? We defined a polynomial function given the zeros. Right? We did it the 2 ways. I showed you how to do it in the calculator, or we used the Venn method. Determine a factored form of a polynomial expression from the x-intercepts of the graph. And the last one, identify zeros of multiplicity greater than 1 and describe the effect of those zeros on the graph. That's pretty close to what we did there. So if you go to the homework, right, on page 293. Right? The 13 through 17, the directions say, find the zeros, then graph the function. I'm telling you, don't graph, just find the zeros. The 19 through 25, the directions say, write a polynomial function in standard form with the given zeros. And I'm saying you could just leave it in the factored form. And the 31 through 34, that says find the zeros, state the multiplicity, like we just did on the last one.